In the last lecture, we have seen introduction to a processor, right? Microprocessor. We have seen the basic introduction for your processor. And coming to the next topic, now let us see one of the processor, right? 8085, the first microprocessor invented by Intel. Before that, you have 4004 processor also, but it performs only 4-bit arithmetic and logical operation. If you go for 4004 microprocessor, it performs only basic 4-bit arithmetic and logical operation, right? Now that has some disadvantages. After that 4004 microprocessor, now 8085 came into picture, right? Now 8085, which is first microprocessor, that this processor only we will study in your syllabus. 8085, which is the basic microprocessor. Now this performs 8-bit arithmetic and logical operation, right? Now what is a processor? It is a central unit of a PC which performs arithmetic and logical operation, right? You know what is arithmetic operation and you know what are logical operations, right? Now processor is nothing but the central part of a PC, nothing but your computer, which performs arithmetic and logical operation, right? Now where we can use processor? Where you require programming. You can use anywhere where we require programming, right? We have seen the basic introduction in previous lecture. Now let us discuss 8085 microprocessor, right? Now this microprocessor, here it will start 8085 microprocessor, which is an 8-bit. It is an 8-bit processor, right? It is an 8-bit processor, and this performs 8-bit arithmetic and logical operation. The name, see, after 8085, 8086 came into picture, right? Now that is a 16-bit processor which performs 16-bit arithmetic and logical operation. You know 16-bit, right? Bit means you know, right? Now this 8085 performs 8-bit arithmetic and logical operation. Now after 8085, 8086 came into picture, which is invented by Intel. Later it is combined with IBM, right? Now that 8086 performs 16-bit ALU operation, arithmetic and logical operation, which are of 16-bit. But here in your syllabus, we will study the basic microprocessor, which is an 8-bit microprocessor, that is 8085, right? Now let us see, as I have said, processor is an IC, right? It is an IC which contains 40 pins, right? Now let us briefly discuss what is the operation of the individual pin, right? 8085, if you see this diagram, now coming to next topic, that is pin diagram of 8085, right? Now before going to architecture of 8085, now let us see the pin diagram, right? As I have said, 8085, it is an IC which contains 40 pins, right? Now this is the structure of your 8085 pin. Now this contains 40 pins, right? Now starting from 1, 2, 3, so on up to 20. On left side, starting from 1, 2, 3, so on up to 20. And here 21, 22, 23, so on up to 40, right? 20 pins are allocated to one side and another 20 pins are allotted to another side, right? Now this is the pin diagram of 8085. Now let us see the individual pins. Total 40 pins are there. Now let us see the operation of those 40 pins, right? Now the first pin, I will briefly explain what is mean by this particular pins. Later we will see its operation, right? After description we will see its operation, right? Now this X1, X2, pin 1, pin 2 contains X1 and X2. Now here here we will connect some circuit, right? Here we will connect some circuit to provide the signal, right? Here we will connect some circuit to provide the clock signal to the processor, right? Now next you have reset out pin at your third pin, and next you have SOD, right? SOD, serial out data. SOD at your fourth pin, which is serial out data. And next you have SID at your fifth pin of your 8085, that is SID, serial in data. SOD stands for serial out data and SID stands for serial in data. And next you have trap, right? TRAP, trap. And next you have RST 7.5. RST 7.5, and next you have RST 6.5, and next you have RST 5.5. All these are interrupts. What are interrupts? We will see later. Trap, RST 7.5, RST 6.5, RST 5.5, and INTR. All these are your interrupts, right? What is meant by interrupt? We will see after this, right? And next you have at your 11th pin INTA, interrupt acknowledgement signal. INTA stands for interrupt acknowledgement signal, which is provided at 11th pin of 8085. INTA, and this bar, which is an active low signal, INTA bar, which is an active low signal. That means this for particular logic 0 this signal will operate, for logic 1 it won't operate. Now what is its operation we will see later, right? And at your 12th pin AD0, right? AD0, AD1, AD1, AD2, AD3, AD4, so on up to AD7 till 19th pin. Starting from 12th pin to 19th pin you have AD0 to AD7. Now what is mean by AD0 to AD7? As I have said, bus, right? Bus is used to transfer the information between the memory and microprocessor, or the processor in bit, or the processor to the input or output device, right? Under that bus we have seen three different types of buses, right? Now what are those? Address bus, data bus, and control bus, right? Now here A stands for address, D stands for data. Multiplex, you know the meaning of multiplex, combining, right? Here address bus and data bus are combined with each other, right? AD0, AD1, AD2, AD3, AD4, AD5, AD6, AD7, right? Now as I have said, 8085 it is an 8-bit processor, right? Now the 8-bit processor which performs 8-bit arithmetic and logical operation, right? Now here the data bits are 8-bit. If you see the data bits which are carried through the data bus, which are of 8 bits, that is 0, 1, 2, 3, so on up to 7, right? And at 20th pin we have VSS, which is nothing but for ground reference, right? Now 21 to 28, right? 21 you have address bit 8th, right? A8, that is 9th you will get starting from 0, and at 22 you have A9, 23, A10, and at 24th pin you have A11, and so on. This will vary up to 28 till 8. Now if you see this pin diagram, now we have 16-bit address lines, right? Bus is nothing but set of lines, right? Now under bus we have three different types of buses: address bus and data bus and control bus, right? Now here if you see this pin diagram, now address bus is of how many lines? 16-bit lines, right? 16-bit of lines are available as your address bus. That means through the address bus you can carry 16-bit address, right? You can carry 16-bit address using address bus. Now if you see the data bus, now how many data bits are available? D0 to D7. That means you can carry 8-bit data through the data bus. This point you have to remember, right? Now address bus for your 8085 microprocessor is of 16-bit, and data bus is of how many bits? 8-bit, right? Since it is an 8-bit processor, it will perform 8-bit arithmetic and logical operation. Hence the data can be carried in between the processor or the memory or processor or the IO devices is of how many bits? 8 bits, right? Since D0 to D7, right? And next you have at 29th pin you have S0, status signal 0. S0 stands for status signal 0, right? And at 30th pin you have ALE, address latch enable signal. ALE stands for address latch enable signal. Now here if you see, address bus and data bus are combined with each other, right? Now if you want to transfer only address bus, lower order address bus, right? Now here you have to transfer through this line, right? But it is multiplexed with data, right? Now you have to separate address bus with data based on this ALE signal, right? Based on this ALE signal is used to separate address bus and data bus, that is AD0 to AD7. How it will separate we will see later, right? Now at 31st pin we have WR bar, which is an bar indicates active low signal, right? WR indicates writing the data, right? WR indicates writing the data. And at 32 pin you have RD stands for reading the data. It will read the data or it will write the data into the memory or from the memory, or into the IO devices or from the IO devices, right? Now these are reading the data and this is writing the data, right? Now at 33 pin you have S1, right? We have status signal 0 and status signal 1, right? Now based on this inputs to this S0 and S1, particular operation is performed. You have a table over there, we will see later, right? And at 34th pin you have IO/memory bar, right? IO/memory bar, input output operation or memory operation, right? A particular operation in the memory, or see if a operation is performing, whether it is from the IO devices or it is from the memory, that is indicated through this pin, right? And at 35th pin you have ready pin, right? What is meant by ready we will see later, right? Now at 36th pin we have reset in, right? You know the meaning of reset in, and that is an active low signal. Bar indicates active low signal, right? Now at 37th pin you have clock signal, clock out signal, right? Now the processor will provide a clock signal to the other signals, to the other devices, right? Now if any other devices want it will want the system clock, now that can be taken through this clock out, right? And next you have VCC, right? At 38th pin you have HLDA, hold acknowledgement signal. HLDA stands for hold acknowledgement signal, right? Now at 39th pin you have hold, right? You have hold signal. What is meant by the hold signal we will see later. Now at 40th pin we have VCC, right? Now in order to operate this particular processor or the pin IC, you need to provide some power supply, right? That is given through 40th pin, that is VCC, right? Now this is the description of the pin diagram. Now let us see the individual operation of the pin diagram, right? Individually we will see the operation of the pin diagram. This is the pin diagram of your 8085, which is a description what is meant by what, right? Now let us see its operation, right? Individual operation of the pin briefly, right? Now what 40th pin, what do you have? Now you have to remember this IC, right? You have to remember this 8085 IC, which is very important, right? Now at 40th pin you have VCC, right? Now we have VCC, right? Now if you want to see, in order to operate this particular IC, we have to provide some supply, power supply, right? Now plus 5 volts, right? Plus 5 volts of power supply is given through this pin, right? Plus 5 volts power supply is given through this pin, 40th pin. Through 40th pin you are giving power supply of plus 5 volts to the 8085 IC in order to operate it, right? Now that is the first pin we have seen. And next we have 20th pin, right? I am writing pin number and also that particular signal, right? And at 20th pin we have VSS, right? Now this is used for ground reference, right? Now this is used for ground reference. At 20th pin we have ACC, VSS, right? And this is used for ground reference, right? Now pin number 1 and 2, pin 1 and 2. Now what are provided at your pin 1 and 2? X1 and X2, right? X1 and X2, right? Now at this particular pin number 1 and pin number 2, we tuned circuit, right? A tuned circuit, you know, like RC or LC, right? Like RC or LC is connected through this pin, right? Now we are connecting the tuned circuit at your pin number 1 and pin number 2, right? Now the internal, in order to generate the signal, right? Now in order to generate the clock signal, right? Now we are providing a tuned circuit such as RC or the LC at your pin number 1 and 2, right? At pin number 1 and 2 we are providing this tuned circuit. Now the internal clock generator Now this oscillator frequency by 2, right? This oscillate there, right? We are providing the tuned circuit like RC or LC. Now this is connected at your pin number 1, that is X1, or the pin number 2, that is X2, right? Now if I and this has a frequency of 6 megahertz, right? Now let us assume, now this has a frequency of 6 megahertz. Now internally it will operate at 3 megahertz. Internally the 8085 operated 3 megahertz. That means we have to provide 2 times of its frequency. We have to provide 2 times of its frequency because the internal clock generator divides the oscillator frequency by 2, right? Whatever the internal clock is there, that will divide the oscillator frequency by 2, right? If you are providing 6 megahertz, divided by 2 will give you 3 megahertz. That means processor will operate at a frequency of 3 megahertz, right? Now if you are providing the oscillator frequency as 8 megahertz, that means if whatever the tuned circuit that you have connected at your pin 1 and 2, now that is providing the frequency of 8 megahertz. Now this oscillator frequency divided by 2, which will give you 4 megahertz. Now this particular frequency is, at this particular frequency the processor will operate, right? Now we have to make sure that we have to provide 2 times of the 2 times of it, right? Now if you want to operate your processor at 12 gigahertz, right? Now let us assume if you want to operate a processor at 12 gigahertz, that means we have to generate the oscillator frequency of 24 gigahertz, right? We have to generate the oscillator frequency at 24 megahertz. Basically it operates in megahertz only, right? Basically it operates in megahertz only. Processor will operate in megahertz only. But what is pin number 1? X1, right? Pin number 2, X2, right? We are providing the oscillator, right? Oscillator, nothing but the tuned circuit like RC or the LC at your pin number 1 and 2. Now what oscillator will do? It will generate some oscillator frequency, right? Now that frequency divided by 2. This operation will done by the internal clock generator of the processor, right? Now if the oscillator frequency is 8 megahertz divided by 2, which is nothing but 4 megahertz, at this particular frequency the processor will operate, right? Now the user has to have an idea about this particular oscillator frequency and the internal clock generation frequency, right? Now meanwhile you remember we are providing the oscillator or the tuned circuit like RC or LC at your pin number 1 and 2, right? At pin number 1 and 2. Now oscillator will generate some frequency. Now that divided by 2 is the operating frequency of a processor, right? Now this is about pin number 1 and 2. We are providing the oscillator at your pin number 1 and 2 in order to give the operating frequency to the processor, right? Now next we have clock out signal, right? Next we have clock out signal, and this is provided at 37th pin. At 37th pin you have clock out signal, right? Now this clock out, now as I have said, now this is the signal used as a system clock for the other devices, right? Now when it is active high indicates 1, right? When it is active high, that indicates 1. That means this signal is used as a system clock for other devices, right? This signal is used as a system clock for other device. When it is active low, active high indicates 1 and active low indicates 0, right? Now system clock you can't use, no operation, right? Now you can't use this as a system clock for other devices, right? Now these are the 5 pins which we call it as power supply signals, right? Power supply signals of a 8085 processor, clock and power supply signals, right? Now these are the 5 clock and power supply signals for your processor, because internally we have clock signal and we are generating some operating frequency for your processor, and next we have power supply. That's why clock and power supply signals R5, right? Now let me briefly explain. At 40th pin we are providing VCC, through which you can provide a +5 power supply voltage to the microprocessor in order to operate it, right? Now at 20th pin VSS, right? Now that is used for ground reference, right? Now at pin number 1 and 2 we have X1 and X2, right? At pin number 1 and 2 we have X1 and X2. Now we are connecting the tuned circuit like LC or RC or any other oscillator at these pins, right? Now what it will do, it will generate some oscillator frequency, right? Now that divided by 2, if it is generating 6 megahertz, now divided by 2 will give you 3 megahertz, right? Now that is the operating frequency of a processor, right? Now that divided by 2 is done by the internal clock generator, right? Now a tuned circuit like LC or RC or any crystal like circuit is connected at your pin number 1 and 2, right? Now that will provide the frequency, oscillator frequency. Now the internal clock generator will divide the oscillator frequency by 2, which will give you the operating frequency of the processor, right? Now through this we are connecting some circuit. Now that will give the oscillator frequency. Now that divided by 2 is done by the internal clock generator. Now that particular frequency after dividing by 2 is the operating frequency of a processor, right? And next you have clock out signal. At 37th pin you have clock out signal. When it is active high, that indicates when it is 1, that this particular signal can be used as a system clock for other devices, right? When it is active low, 0, right? When it is active low, which indicates 0, you can't use this signal as a system clock for other devices, right? Now these are the power supply and clock signals of your 8085 microprocessor, right? We have seen 5 pins till now. One is VCC, VSS, X1 and X2, and another one is clock out signal, right? Now from pin number 12 to pin number 19, right? Pin number 12 to pin number 19. Now what do you have? AD0 to AD7, right? AD0 to AD7. Pin number 12 to pin number 19, you have AD0 to AD7. Now here the data bus is of how many bits? Now the data bus is of how many bits? D0 to D7, which is nothing but 8 bit, right? Now here if you see this data bus is of 8 bit data bus. Bus is nothing but set of lines, right? Now here the address bus. Now here you have address bus, that is A0 to A7, which is also 8 bit, right? Now these two are multiplexed, right? From pin number 12 to pin number 1, pin number 19. Now these two are multiplexed, right? From pin number 12 to pin number 19. Now these two are multiplexed. Lower order address and data bus. Data bus, anyhow it is an 8-bit processor. Now it contains 8-bit data, right? Now data bus will carry that particular 8-bit data, right? Now here the data bus is of 8-bit, which is multiplexed with lower order address bus, right? Which is multiplexed with lower order address bus, right? Now together it is operating, right? Now I want to transfer only A0 to A7 through this bus, right? Now what I have to do, we have to use the signal address latch enable signal, right? Now address latch enable signal, based on this signal only you can transfer whether it is address or it is data through this particular AD0 to AD7, right? Now AD0 to AD7 it will transfer multiplexed, right? If you see that all address, lower order address and data bits are multiplexed, right? Now that will carry lower order address and also data bus, right? At a time it can't carry the address with data bus, right? We have to individually it will carry, right? Now when ALE is 1, right? When address latch enable is 1, when it is active high indicates when it is 1. Now this will enable address bus, right? when ALE is 1, now this particular AD0 to AD7 can carry lower order address, that is A0 to A7, right? When it is 0, which is nothing but active low, right? Which is nothing but active low. When ALE is 0, which is nothing but active low, and through this you can carry data bus. It enables data bus, right? It enables data bus which will carry D0 to D7, right? Now through this ALE only we can carry whether it is address or whether it is data from AD0 to AD7, right? Now ALE is provided at your 30th pin. This is provided at your 30th pin, right? From pin number 12 to pin number 19 we have AD0 to AD7, that is 8-bit data and 8-bit data bus, and another one is lower order, right? Lower order address bus, that is A0 to A7, right? Now this particular set of lines can carry lower order address and also can carry data bits, but right now at a time it can't carry together, right? At a time it can't carry lower order address and data bits, right? Now it has to carry individually, right? Either it has to carry lower order address or it has to carry 8-bit data, right? Now that operation is decided by the ALE signal, address latch enable signal, right? See, AD0 to AD7 lines can't carry lower order address and 8-bit data at a time, right? It has to carry individually, that is either lower order address or 8-bit data, right? 8-bit data. Now that particular whether to carry lower order address or whether to carry 8-bit data, now that particular operation is decided by the address latch enable signal, right? When it is active high, that indicates when ALE is 1, right? When it is active high, when ALE is 1, you can carry address lower order address through these lines. AD0 to AD7 you can carry lower order address lines, that is A0 to A7, right? When it is 0, when address latch enable is 0, now you can carry data bits through these lines, right? You can carry, you have AD0 to AD7, through these lines you can carry data bits, right? Now whether to carry lower order address or whether to carry data bits, that operation is decided by the address latch enable signal. When ALE is 1, AD0 to AD7 lines will carry a lower order address. When ALE is 0, AD0 to AD7 lines will carry data, that is 8-bit data, that is D0 to D7 bits, right? Now this is how these are interrelated to each other, ALE and AD0 to AD7. When it is 1, A0 to A7 bits are carried over AD0 to AD7. When it is 0, D0 to D7 bits are carried over AD0 to AD7 lines, right? Now this is about your ALE address latch enable signal, right? And next we have from 21 pin to 28th pin, right? From 21 pin number 21 to pin number 28, what do you have? A8 to A16, right? A8 to A15, right? Now this will carry higher order address, right? From A8 to A15, right? The upper higher order address, right? Now we have A16, A15, so on up to A0, so on up to A7. Now here assume A8, right? Now here A7 to A0 we have covered under AD0 to AD7, right? When ALE is 1, right, you can carry lower order address through AD0 to AD7 lines, right? Now here there is no multiplexing of your address lines with data lines, right? Now directly it can carry higher order address, right? From A8 to A15 this is your higher order address, right? Which will carry higher order address, right? Now we have 16-bit address lines, right? If you see this structure, you have 16-bit address lines, that is A15 to A0, right? Now you have 8-bit data lines, right? You have to remember this, these are very, very important, right? You have 8-bit data lines, that is D0 to D7. You have 16-bit address lines, 8-bit data lines, right? Lower order address is multiplexed with data lines depending on the ALE signal, right? Depending on the ALE signal, whether to carry address, lower order address, or whether to carry data bits is decided on the decided by the ALE signal, right? Now from pin number 21 to 28 we have address lines A8 to A15. Now this will carry higher order address, right? Now here you have how many address lines total? 16 address lines, and you have data lines, 8 data lines, right? Now we have 16 address lines and you have 8 data lines. Now 2 power, you have to, this is very, very important. Now 2 power address lines, number of address lines, right? 2 power number of, I will say, now we have 16 address lines, right? You have 16 address lines and you have 8 data lines, right? And you have 8 data lines. Now 2 power number of address lines, 2 power number of address lines will give you the memory of a processor. You have to, this is a very, very important. 2 power address line will give you the memory of a processor, right? 2 power address lines will give you the memory of a processor. Now how many address lines are present for your 8085? 2 power 16, right? Now this is the memory of a processor. That means to that extent it can store the data bits, right? Now 2 power 16 you can find out, right? 2 power 16. What is 2 power 16? You can find out 2 into 2 power, see, 2 cube into 2 cube into 2 cube, 3 3 9, to 2, right? Now here 2 3s 8. Now 8 into 8 into 8 into 2, right? Now 8 8s are 64, right? Now 8 8s are 64 into 60, right? 64 into 64 into 16, right? You can calculate this, right? You can calculate this. Now this 64 into 64 into 16, now this will give you the 64 kilobytes of memory, right? 64 kilobytes of memory. If you want you can do it, right? 2 power number of address lines, right? 2 power number of address lines will give you the memory of a processor. Not only this, this is valid for any other processor. 2 power 16, right? Two power 16, right? 2 power 16 will give you the memory of a processor for your 8085, that is 64 kilobytes. You will get 65 536 exactly, but generally we will consider it as 64 kilobytes of memory, right? Now if I consider 8086 processor, right? If I consider 8086 processor, now that processor will contain 20 address line. Now that processor will contain 20 address line. Now what is the memory of 8086 processor? 2 power 20, right? After calculation you can directly give the memory of a processor, right? Now you have to just remember one point here. Two address lines are 16 for 8085 and data lines are 8 for 8085. Now here data lines are 8 for 8085. Now here 2 power number of address lines will give the memory of a processor. 2 power number of address lines will give the memory of a processor, right? Now this is about how to calculate memory of a processor, that is given by the 2 power number of address lines, right? Now that is about your address lines we have seen, and we have seen ALE also. And next let us see RD bar, which is provided at your 32 pin. At your 32 pin we have RD bar signal, which is nothing but read signal, and at 31 pin we have WR bar, right? At 31 pin we have WR bar, and at 32 pin we have RD bar, read signal and write signal, right? Now these signals are these are active low signals, right? If you see this, these are active low signals, right? These two signals are active low signals, right? Now when it is 0, when RD signal is 0, that means you can read the data, right? When it is low, you can read the data from the memory location or the IO devices, depending on that, right? You can read the data. You can read the data from memory location via data bus, right? From the memory location or IO devices from via data bus, right? Now when it is 1, you can't read the data, you can't do the read operation, right? Now similarly the same thing followed for your WR bar signal, right? Now when it is 0, you can write the data to the memory location or the IO devices via data bus, right? Now here data bus is bidirectional, either you can take the data or you can give the data. Data bus is bidirectional here, right? Now the read signal is used to read the data from the memory location or the IO devices, and the write signal is used to write the data from to the memory location or the IO devices, and all this writing and reading the data is done through the data bus, right? Now this is about read signal and write signal, right? And next we have IO/memory, right? And next we have IO, input output or memory bar, right? Now this is provided at your pin number 34, IO/ or memory bar. Now this is provided at your pin number 34. When it is 1, right? When it is 1 and when it is 0, right? Now this indicates IO operation when it is 1, input or output operation when it is active high, and when it is 0, this indicates memory operation, right? When it is IO/memory bar, which is 34, provided at your 34th pin of a processor. Now when it is 1, now this indicates IO operation when it is 0, and that indicates memory operation, right? And next you have S0 and S1, right? Now these are, as I have said, what are S0 and S1? Status signal, right? Status signal which shows the operation of a processor. Status, it gives the status of a processor, whether which operation is doing by the processor. That status is given by the signals S0 and S1, right? Now based on this IO/memory and S0 and S1, you have a table, right? Whether the microprocessor is performing read operation, or it is performing write operation, or it is performing some other operation. Now that is decided by these signals IO/memory and S0 and S1, right? Now let me draw its table. Now IO/memory bar, and you have status signal S1 and you have status signal 0, and what is the operation that is performed by the processor, right? Now when all are 0, right? When all are 0, right? Now here when IO/memory bar is 0, which operation? Memory operation, right? Now when status signals are 0, right? When status signals are 0, now microprocessor is under halt condition. It is under halt condition because when two status signals are 0, now that indicates processor is not doing any operation, right? Now when it is 0, 0, 1, right? Now when it is 0 0 1, now what it indicates, which operation it is? Memory operation, right? Now through the memory, either you can read the data or you can write the data, right? Now memory stores the program, that is set of instruction in the low level language, right? Now if you, from that memory I can read the data or I can write into that memory, right? Now whether to read the data or whether to write the data, that is decided by this status signal. Now here which operation it is? Memory operation. When S1 is 0 and S0 is 1, right? Now here the operation is memory write, right? When S1 is 0 and S0 is 1, when the status of the signal is 0 1, that means microprocessor is performing the operation of writing, right? Now since it is 0, memory write operation, right? And next we have 0 1 0, right? When S1 is 0 and S0 is 0, that indicates read operation, memory read operation, right? Now when 0 1 1, right? Now when 0 memory operation, here it is memory operation, and when it is both are 1, right? Now where you will fetch the opcode? Opcode is nothing but binary form of instruction, right? Now where we have seen where we the 3 steps of your processor, that is fetch, decode and execute, right? Now where you are fetching the opcode? From the memory, right? That's why it is 0. Now when both signals are high, now that indicates fetching of opcode fetch, right? Opcode fetch, right? And when it is 1 0 1, right? When it is 1 0 1 0 1, which operation it is? Write operation. But here it varies, IO write operation, right? Now here you will get input or output write operation. When it is 1 1 0, now IO read operation, right? When it is 1 1 0, IO read operation. Now what is left out? All ones, right? Now interrupt acknowledgement, right? Interrupt acknowledgement signal. Now what is interrupt acknowledgement signal? We will see later, right? Now meanwhile you remember, right, when IO slash coming to 34th pin, IO slash memory bar, right? IO slash memory bar, when it is 1, it indicates IO operation. When it is 0, it indicates memory operation, right? And next we have status signals S0 and S1, right? Now based on this you have a table. Now S0 and S1 will give the status of a microprocessor. That means whether it is writing the operation or whether it is reading the operation, that particular status is given by the status signals S0 and S1, right? Now when IO slash memory bar is 0, which indicates memory operation, right? When all are 0, halt condition. Microprocessor is under halt condition. When it is 0 0 1, right? When it is 0 0 1, now when IO slash memory bar is 0, it indicates memory operation. Now when status signals are 0 and 1, that indicates write operation, right? Right? Memory write operation. When it is 0 1 0, memory read operation. When it is 0 1 1, opcode fetching, that is from the memory. We will fetch the opcode from the memory, that is opcode fetch for 0 1 1. When it is 1 0 1, IO write operation. When it is 1 1 0, IO read operation. When all are ones, interrupt acknowledgement signal, right? That is interrupt, acknowledgement. What is meant by acknowledgement? To accept, right? Now interrupt acknowledgement is nothing but interrupt signal. We have different types of interrupt signal. That particular, whether it may be any of those 5, that particular signal is accepted by the processor, right? Interrupt is accepted by the processor, which is nothing but interrupt acknowledgement signal, right? Now this is about IO slash memory bar, right? IO slash memory bar and S0 and S1, right? Now coming to next signal, and next signal ready. Now this is provided at 35th pin, right? This is provided at 35th pin. Next signal is ready signal. Now this is provided at the 35th pin, right? Now this will sense the microprocessor. This is used by the microprocessor to sense whether the output devices, right, peripherals are nothing but the output devices, are ready for the data transfer or not, right. Now when it is one, output devices are ready for data transfer, right. When it is one, output devices are ready for data transfer. When it is not ready, when it is 0, output devices are not ready, right. Now ready is the signal that is used by the processor in order to sense whether the output devices are ready for the data transfer or not, right. And next you have serial input data, right. SID, this is provided at your 5th pin. SID, serial in data, which is provided at 5th pin, right. Now this input signal is used to accept the data serially. Serially is nothing but bit by bit, right. Now this input signal is used to accept the data bit by bit from external devices, right. Now when it is 1, it accepts data serially. What is mean by serially? 1 by 1, bit by bit, right. 1 by 1, bit by bit. It accepts data serially from external devices, right, from external devices, right. Now when it is 0, no accept, right, no acceptance. It won't accept data serially from external devices, right. Now coming to SOD, which is provided at your 4th pin, right, serial out data, right. Now when it is 1, right, it when it is 1, it sends the data output, right, it sends the data serially bit by bit to the external device, right. Now sends data serially, it sends data serially to external devices, right. No sending, right. When it is 0, no sending, right. Now this is about serial out data. Now coming to next signal, hold. Now this is provided at 39th pin, hold signal, right. Now this signal when it is 1, right. Now when it is 1, see this signal when it is 1, this signal indicates another devices, right. It may be any devices. Now this signal indicates another devices is requesting for the use of address bus, data bus or control bus, right. Hold signal, that means processor has to release its control over address bus, data bus and control bus in order to get use them by the other devices, right, in order to get use them by the other devices, right. Now hold signal indicates another, when it is 1, right, when it is 1, other devices is requesting for address bus, data bus and control bus, right. When it is 0, not requesting, right. Now this is about the ready signal, SID, SOD and hold signal, right. This is about the ready signal, SID, SOD and hold signal, right. Now ready is used by the microprocessor in order to sense whether the output devices are ready for the data transfer or not. When it is 1, output devices are ready for the data transfer. When it is 0, they are not ready. Now coming to SID, serial input data, right. Now this will accept the data serially from external devices, right. When it is 1, microprocessor will accept the data serially from external devices. When it is 0, it won't accept the data, right. Now SOD provided at your 4th pin. Now when this will send the data serially to the external devices, right. Now when it is 1, microprocessor will send the data bit by bit to the external devices. When it is 0, it can't send the data. Now coming to hold signal, right. Now this signal indicates that other devices one is requesting for the use of address bus, data bus and control bus, right? Now when it is 1, it indicates that other devices is requesting the for the use of address bus, data bus and control bus, right? When it is 0, they are not requesting for the use of address bus, data bus and control bus, right? Now this is about the hold signal. Now coming to next signal, hold acknowledgement, HLDA. Hold acknowledgement. What is mean by acknowledgement? Acceptance, right? Now when it is 1, hold signal is accepted by the processor. That means request, right? What is mean by the hold signal? My other devices is requesting for the use of address bus and data bus, right? Now whether to accept hold signal or not, that depends on the processor, right? Now when that is given by this through hold acknowledgement. When it is 1, hold signal is accepted by the processor. That means it will release its control on address bus, data bus and control bus so that other devices can access it, right? Hold signal is accepted by microprocessor. When it is 0, no acceptance, right? Hold signal is not accepted by the microprocessor, right? Now coming to next signal, that is reset in bar, right? Now this is an active low signal. Reset in bar is an active low signal, right? Now when it is 0, this sets PC to 0. What is PC? Program counter, right? Now what it will store? It will store the address of the next instruction that is to be executed, right? Program counter will store the address of the next instruction that is to be executed, right? When reset in is 0, that means when it is under active low condition, now it sets the PC to all zeros. H indicates, say microprocessor will operate in hexadecimal, that's why I have represented H here, right? Now when it is 0, reset in is 0, it sets the program counter that to 0, right? Totally the program counter, whatever the address is stored in that particular program counter will be vanished for the active low of reset in, right? Now when it is 1, program counter can't be reset, right? Now coming to next signal, that is reset out. Now this is provided at the 3rd pin, right? This is provided at 3rd pin of the processor, right? Now this pin indicates the processor is being reset, right? Now this pin indicates the processor is being reset, right? Now once the processor is reset, then all the connected devices must also be reset. Now this is done for active high. When it is 1, the microprocessor will get reset, and whatever the devices connected to that microprocessor also, that will get reset, and that is done for active high, right? That is done for active high, right? Now let me briefly explain. Hold, HLDA stands for hold acknowledgement signal. What is meant by the hold signal? It will give the information to the processor that other devices is requesting for the access of address bus, data bus or the control bus, right? Now whether to accept hold signal or whether not, that is up to the processor, right? Now when it is accepting the hold signal, now that will provide an active high signal over HLDA. Hold acknowledgement. Acknowledgement is nothing but acceptance, right? Now when hold acknowledgement signal is 1, which indicates hold signal is accepted by the processor. When it is 0, it is not accepted. Now what is hold signal? Requesting the request is made by the other devices for the use of address bus, data bus or control bus, right? Other devices wants to use address bus, data bus or the control bus, then it will generate hold signal, right? Now once the processor will accept the hold signal, now that information is given through hold acknowledgement signal, right? Now coming to reset in bar, which is an active low signal. When it is 0, it will set the program counter to 0. Now what program counter will do? It will store the address of the next instruction, right? It will store the address of the next instruction. Now when reset in bar is 0, it will, whatever the address that is stored in the program counter, that will get vanished. That is for active low. Since it is bar, that is done for active low. Now coming to reset out. Now the microprocessor is resetted for, that means microprocessor will get reset for active high, right? When it is 1, that is logic 1, the microprocessor will get reset, right? Now when the processor gets reset, whatever the connected devices are there, that also will get reset automatically, right? When it is active high, the processor will get reset. Now whatever the devices that are connected to the processor, those also will get reset, and that is done for the active high signal, right? And the next, you have next left out signals are, before that let me say interrupt, right? What is meant by the interrupt? To stop the process, right? To stop the process, right? Now a user want to stop the process of the microprocessor, right? Whatever the process it is doing, I want to stop that process, right? Then user has to generate interrupt signal, right? Interrupt is nothing but stopping the process, right? Now when a user want to stop the process, then the user has to generate interrupt signal, right? Now we have interrupt is nothing but to stop the process. Now we have different types of interrupt signal, that is RST 6.5 and RST 7.5 and RST 5.5, and you have INTR and you have trap, right? Now these are the, and you have interrupt INTA bar, which is an interrupt. These are the left out pins, right? INTA bar, these are the left out pins. Now these are the interrupts through which the user can interrupt the process of a microprocessor, right? Through which the user can interrupt the process of a microprocessor. See, RST 6.5, 7.5, 5.5 in INTR. All these 4 are maskable interrupts, right? Where trap is non-maskable interrupt. Now what is meant by the maskable interrupt? We can disable interrupt by writing some instruction. We can disable this particular interrupt, right? Whereas trap is a non-maskable, we can't able to disable the trap, right? Now interrupts, see, when a user want to stop the process operation of a processor, then the user has to give the interrupt signal. Either it may be 6.5, 5.5, 7.5, INTR or trap, right? Now once the trap interrupt is given, you won't be able to disable, right? Now the remaining 4 can be disabled. That's why it is called maskable interrupt, and trap is called non-maskable interrupt. Now INTA bar, interrupt acknowledgement signal. When it is 0, interrupt is accepted. INTR interrupt is accepted, right? When it is 1, interrupt is not accepted by the processor, right? Now interrupt is nothing but to stop the process of a microprocessor. If a user want to stop the process of a microprocessor, then the user has to give the interrupt signal, right? Now the 5 different types of interrupt signal available in your 8085, that is RST 6.5, 7.5, 5.5, INTR, trap, right? Now 6.5, 7.5, 5.5, INTR are the maskable interrupts. That means once those are generated, we can disable by giving some instruction. That's why those are called maskable interrupt, right? Where trap, once the trap is generated, you won't be able to disable the that particular interrupt. That's why it is called non-maskable interrupt, right? Now one INTA bar, which indicates interrupt acknowledgement signal, right? Now once the interrupt is acknowledgement is nothing but acceptance, right? Now for 0, since it is bar, for 0 it indicates interrupt is accepted by the processor. For 1, it indicates interrupt is not accepted by the processor. Meanwhile, you remember you'll have a separate topic on interrupt. Meanwhile, what is interrupt? To stop the process of the microprocessor. We have 5 different types of interrupt. Some are maskable,
that means we can disable by writing the instruction. Some are non-maskable, that means we can't able to disable once those are generated, right? If the interrupt signal is accepted by the processor, we will active low signal on the INTA, interrupt acknowledgement signal. If it is not accepted, active high, right? Now this is about the pin diagram of a 8085 microprocessor. In the next lecture, we will see the architecture of 8085, right? Thank you.